let's see how the projected population is going to get distributed in the area. Okay, this is called the ward-wise population by equivalent area method. So consider this case. In 2011, the population of a place was 30,450, and the future projected population for the year 2046 is 40,631. Now you can choose any method or the average of all the methods that we have just learned. The ratio of this works out to be 1.334. Okay, so now all I am saying is the area that we have to cater will have a maximum population of 40,631, and currently it is having 30,451. So now this increase in population will not be distributed uniformly over the whole area. Rather, it may follow some specific pattern. Some areas may be more denser than the others, and other may be differently populated than rest places. So let's learn about this. Now, this is a land use map. A land use map is generally a map which tells you that how a particular area is subdivided into various kinds of land usage, whether the land there has been used for residential purpose, for commercial, industrial, playgrounds, public utility, or anything. Now this is the area for which we need to design the water distribution system for. But as we have already seen that there is about a 10,000 increase in population till the year 2046. Now again I am saying that this is not going to get distributed uniformly in this area. So there must be a methodology by which we can tell which areas will get more population and which will get lesser one. So before proceeding further, let's understand about the ward system. What are wards? Now the places for which we may need to design a water supply system may have some outer boundaries, and this is how the outer boundaries may look like. Okay, to give you some perspective, let me give you an example. So consider India. Now there is this place in India. Now India is subdivided into various states, right? There are 28 of them, and this is one such state. So let's say that there is some place in this state in which we want to forecast the population for. So from a country, we came to a state, which is a subdivision of a country. Then we move on to the internal divisions of a state, which here are known as districts. So from country, we came to state, and from state, we came on to districts. Now this district will have many cities. So here is one such city, and for this city we need to design the distribution system. Okay. Now this city again has several divisions in terms of wards. Okay. So in a nutshell, any area for which we are going to design a water supply system for should have a subdivision which is generally decided by the municipality of that area. Okay, this is done for better administration and other things. So you should get a map of this subdivision. This in India is called as wards. So you should get a ready-made map of this place, this ready-made map of these wards boundaries. And if you don't have a ready-made ward boundary, you can digitize it using georeferencing from a hard copy that you may have. Right? So we have understood the concept of wards. So ward is basically a subdivision of an area for which we are going to design the water supply systems for. This is very much relevant in context to urban water supply systems, right? Now that we have understood wards, so let's divide this area into a number of wards. So the diagram, so now you can do all these things in any GIS app, for example ArcGIS or QGIS. So all you have to do is keep creating shapefiles you all might be using, and even if you don't know, you can just do a simple Google or YouTube search and you will get to know the basics, right? Now I am superimposing a layer of wards on this map. That is, on this very map I am going to add the boundaries of the various wards. So obviously it is a digitized shapefile. So this is how it will look now, right? So you can see the subdivision of this place into various wards. Okay, if we remove the land use map, this is how the wards look like. Now I'm going to present you with a data that we have worked on, and this will just clear out all the methodology involved in this process. So you can see that in the first column we have certain wards and the total number of such wards is 23. However, you can see that the wards do not start from 1. It starts from 22, 16, 21, 5. Let me point my arrow here. 22, 16, 21, 5, 20. Okay, it should start from 1, 2, 3, 4, 5, 6. But it is arranged in a different manner. Why is it so? We will learn in a little bit. Now with each associated ward, there is a corresponding area. This area is in hectares. So how have we calculated this area? This will either be given to you by the place where you have collected the ward data from, or these save files. These can be easily used to calculate the area of each wards. Tools are available in any GIS software, so you can easily extract the area of each wards. So we have got the area of each ward. Then the population of each ward is given here. This data you will get from the place where you collect the census data from. It is also available with the city development plan or the urban planners of your city. Now based on this, we calculate the population density, right? So what is the population density here? So it is population per unit hectare. So you can simply divide this population by the area and you will get these values. Now you have to calculate the type of land use from GIS map. So here we are going to divide the land use into 4 categories: residential, public, industrial and no man's area. This no man's area includes roads, etc. So how are we going to do this? Again, we have to take use of GIS app. So let's say you are processing this shapefile, this word, into the GIS app, and you want to calculate the area of this yellow place, this violet one, and then this green one. So all these 3 can be summed up differently. Now we do the exercise for all these places, and then we will get a bifurcation of the residential area, the public area, the industrial area and the no man's area. Okay, so this up to here it is clear. Now here is the concept of equivalent area. So what is this equivalent area? So to calculate the equivalent area, you have to give various weightages to these units that are there. Okay, and what are these weightages? Let me elaborate. Now here is the rationale behind the calculation of equivalent area. So you have to take the weightage for residential area as 1. Then for the public area you have to take the weightage as 0.25, for agriculture area 0.1, and for no man's area 0. Obviously, because in no man's area like roads, rails, there is no population going to reside. So there the equivalent area for a water supply will be 0. Now keeping these values in mind, we will calculate the equivalent area in the table. Now by a simple calculator, if you calculate 83.4 times 1, 11 times 0.25, 0.1 times 0.1 and 3.1 times 0, it will give you a result of 86.12. So you have values for all the 23 words. Now based on this equivalent area, now we calculate the population density once again. Okay, so now this equivalent area divided by this population. So here you will again get some ratio. Now you can see that this ratio is arranged in a increasing or a ascending order. Okay, this is the lowest value and the last one, that is 146, is the, and the last one, that is 146 in this column, is the maximum. So now you can imagine why this words have been arranged in such a manner. So it clearly means that word number 22 has the least population density, while 146 has a maximum population density, right? Now based on this, we have to define a certain criteria, that which areas are to be considered as high density areas and low density areas. So let us say that 146 is our saturation level population, that is in ward numbers 6 and 4 we have achieved the saturation level of population. Okay, so areas lesser than these values will be considered as less saturated, or in terms of the codal values it will be known as high. Then from there you can go to medium, and then from there you can go to low. So this categorization has been done on this criteria. Now this can vary from project to project and from person to person. However, we can use the codal recommendations. So since this is not a very fixed value, so I'm just explaining you the rationale behind it. Again, it is not necessary that every project will have a maximum of 146 and minimum of 13.57 only. Okay, so this thing will vary, but you should understand what logic is working behind it. So based on this has been defined as low, medium, high and saturated. So the ultimate aim of ours is that all these places can go to a maximum saturation of 146 only, right? And ward numbers 6 and 4 have lesser tendency to increase its value. Okay, now we start to forecast the population. So here the density has been taken as 25. So how has this 25 been reached? Let us go to the first slide. So the ratio was 1.334. Now this is the ratio of the current population to the future forecasted population. So let's say that if your density is 13.57 right now, so if you multiply 13.57 by this 1.334, what value you will get? It is going to be somewhere around 18. However, for convenience we have taken this value as 25. Okay, again, if in the next iteration if we need, we can reduce it also. So now similarly we will multiply it by this and we will give some values on the density. Now based on this density, if we multiply it by the equivalent area, this is what the population that will reside in ward number 22, right? We will do the exercise for all the wards, but now you can see in the bottom the final population tally is 46,020. which is more than what we have already projected. It was somewhere around 40,600. Okay, so now this is happening because we are giving some factor which is more than what is required. Okay, so we will reduce the factors. Try reducing the factors in the middle areas. Try reducing the factors in the medium density places. For example, here if we have reduced to from 55 to 50 and then further to 45. Here we have reduced from 70 to 60 and then further to 55. So doing 1 or 2 or 3 iterations, we got population which is in the range of what we have already forecasted. So now what we have done, let's recall it. So we projected the population using any of the methods, standard methods. Now we need to distribute this population in the project area. Okay, to distribute it, we do the exercise that is given here. Once done, now we have a population density map of different areas. Now if we put this data into a map, this is how it will look. So the areas in pink are having high density. Then there are areas in green which have low, and areas in red having saturated, right? So once you get this data, so what you can do is, after laying the pipelines, it will become very easy for you to distribute this population, right? Because now you don't have to distribute equal amount of water demand on each node. Rather, the nodes falling in the respective ward boundaries will be decided by its existing conditions. So in a nutshell, what you can do is, once you have forecasted the population by any method, there will be two criteria that will be deciding the distribution of your population into wards. The first one is, what is the current density of that area, and then the other will be, what is the growth potential of that area, right? And here is the methodology which we have used to calculate all those two. Okay, so in any forecast methods, the two things that we will be using is density and growth potential. Now using this concept and a little bit of variation, we will try to do one more example using our own Excel sheet. Now today we are going to do an actual exercise, and I will also be giving you an design sheet from which you can automatically forecast population, and you can also customize that sheet according to your own needs by just doing some tweaks and modifications. So today I am actually going to explain you about a project which we did in 2021, and now the project has started last year 2023, but I will be using some hypothetical names and diagrams in order to make your understanding easier. Now let us call this place as the FPI city. So this is the outer boundary of this place. Now let us divide it into wards. So this is how the wards look. Don't go by size. The bigger ones may be a bit smaller. I have just drawn the rough sketch of this city. And then let's count how many wards are there. There are actually 18 wards. So I have illustrated them one by one. Now in normal practices, what happens is, we are generally given to design systems for existing cities, But sometimes what may happen is some additional area may also be said to design in your project. So this is the administrative boundary of the city. However, 2 more areas were added to it. You can say 2 more wards. So ward number 19 and 20 were added, and this is how they looked, right? So let us name this as ward number 19 and 20. Now the problem here will be with respect to the population forecast, because similar data was not available for ward number 19 and 20, right? So let us see what data is actually available for all these wards. So if you consider only the 18 wards, this is the data that was available. 1971, 1981, 1991, 2001 and 2011 census population was available. But for areas 19 and 20, the same was not available. It was only available for the year 2011, right? So before we go to the 19 and 20 ward, let us first see a detailed bifurcation of the area and the ward-wise population of these 18 wards. So this is the data, right? Let me illustrate you a little bit better. Okay, so this population of 2011 was distributed in such a way in the 18 wards, where the area was given, ward name was given, and the population as per the 2011 census was also given, right? Now if we include the wards 19 and 20, this is what the picture was. So for 19 and 20, the populations earlier to 2011 was not available, right? But for 2011 it was available. So this gives a major challenge in forecasting. How we will solve it, we will see it when we do that. So as per the new data, now the 2011 has 2 values, 15, 56,044 and 60000, that is 60,000. Now this is the design aid that we have created. You can get it from the description below, and it has a password. So it will open only with the registration number that you have received on your email when you purchased it. Or you can mail us at queries.fpi@gmail.com. Right. So there are 6 links here. The first one is for codal provisions. So in case you want to refer the codes for population forecast, you can click here and refer to the codes directly from here. Then you can check the theory involved in this case, but I think these will not be required because we have already discussed all these things in great depth in the last 2 lectures. Then you can also check the census of India. If from clicking on this link, if your country's data is missing, that is if you are not from India and somewhere else, and you are not getting these things, these datas, you can leave a comment and I will try to find it for you. Now done with the 3 links from the first row, we move to the second one. So here the sheet is for population projection. Now we fill the data for the base year, mid year and design year. Now we fill those data. So the base year is 2023 because this is when the project got completed. Mid year, that is the intermediate year, is 2038, and then the ultimate design year is 2053. And this was the census population. For now, let us put both these populations for 2011. We will see how to deal with it. In case you want to make any changes with respect to the structure and the calculation formulas, you can do so if you know basic Excel. Let me just illustrate you what is there in these formulas. So here 5705, that is the decremental increase. This has been calculated with the difference of these two. Okay, let me show you, right? You can see here, you can also visualize it from here. Same is true for all the elements in this row. For this one also, you can check that, right? Now this is the rate of growth, which is the difference divided by the previous census population. Okay, for all the rows, and then we have multiplied it by 100, correct? So now the average decadal increase is 11,025. Now this 11,025.5 has been calculated by taking into account this 2011 population and not this one, okay? But the final arithmetic increase formula, that is P, let's say we want to calculate the population for 2021. So the formula will be 2021 population equals to the population of 2011 plus my n, which is the number of decades, into this value, okay? So here the 2011 population now will be 60,000 because we are calculating the population over and above the cumulative new area, right? So it will be 60,000 into the number of decades, that will be 1 because 2021 minus 2011 equals to 10. So 60,000 into 60,000 plus 1 into 11,025. So which will be 71,026, right? Let us check this value if we have calculated. Yeah, it is 71,026. Similarly for 23, 25, 36, 38, 43, and the ultimate year is 53. Now in case you want to calculate it for a different year, you can change the values. Let me show you. So here, let's say you want to calculate the population for 2024, you can change it to 2024, and then you will have to make a modification here. 2023 instead we can write 2024 minus 11. So this will automatically encounter the change here. This is the formula. Now this is about arithmetic increase method. Similarly, the population for incremental has been calculated, and then the geometric, then APDI method. All these methods are not required, but in some projects we have done this. That's why I have made the sheet like this. You can always follow the CPHEEO methods to calculate your population. Then this uses the simple graphical method. These graphs will automatically get plotted, and then there is a comparative analysis of all the methods that we have learned till now. So we can see that in the ultimate year, graphical method has the highest population. So for new and areas which has high capacity for growth, we'll use geometric increase method. You can also see the comparative analysis with a graph for different methods. So till 2053, again we can validate that geometrical increase will have the highest population. Now we go back to the main screen, and then we see the ward-wise bifurcation. I have already pre-filled this data. So this will be the area of each ward, then the ward name, and then the population in 2011 for all the 20 wards. Now this will be the density. We have already illustrated about in lengths how to calculate the density, but still you can see it's E3 by C3, that is this one, this population per unit area. Then comes the growth potential and factor based on density. Okay, this is the same thing that we have learned in the last video. We can use the same GIS methods to calculate this index based on this I have given here. So if it is a very high density place, so the factor assigned has been 2, that is more the density, lesser the weight. Okay, again we have the factor for potential growth. Okay, now we assign these values. These values are again subjective and may vary from designer to designer. Ultimately your firm has to design and the client. So this is the combined factor, and then from this we get the population for 2023, 38 and 53, right? And the final populations for 23 is 94,507, 1,37,641 for 2038, and 1,80,774, that is the ultimate population. Now we move on to the demand calculation, right? So demand calculation is pretty simple. We have to just consider 3 to 4 more factors. So again I have listed the ward number, ward name, then there is this area, population for 2011, and then the calculated population for 23. We add 10% floating population, that is as per the CPHEEO norms. If you have not referred to the codal videos, I will be uploading it in the next video. Then 2038 and it's floating, 2053 and it's floating. right? Then we can calculate the water demand. If you are having any doubts or any problems on how these things are getting calculated, you can just click here and observe the formulas, but it is pretty simple. Right, so above above the floating population, we are the unaccounted water loss, that is the losses that will be happening during the various stages of transmission. So that will be 15% of the total demand, and then we also include the fire demand. So this adds up to a final demand of 16.98 mld in the year 2023, 24.49 in the year 2038, and 31.97 in the year 2053. So I think this concept is clear now. We have talked in depth about how to calculate the forecasted population and demand. In the next video, we will see how to solve a small network, and then we will move on to the video for codal provisions. Thanks for watching. Have a nice day.